My name is Julissa Juarez. I am an REU student at the University of Washington currently, interning with the Ginger Lab. And today I'm going to be presenting my project looking at defect passivation in formamidinium, cesium, tin, germanium halide perovskites. So let's get started. So first of all, perovskites are a class of semiconductors that are very useful for optoelectronics, and they're part of a new generation of photovoltaics. A halide perovskite crystal lattice has a generic chemical formula of ABX3, where A is a monovalent cation, B a divalent metal cation, and X a halide anion. And so in my project, we synthesized a tin-based perovskite and tin-germanium-based perovskite and characterize the effects of tin-germanium alloying via UV-vis absorption, photoluminescence spectroscopy, time-resolved photoluminescence, and hyperspectral microscopy imaging. So recently, tin-based perovskites have been receiving significant attention as ideal candidates for photovoltaic devices. The main challenge, however, is their instability in ambient air due to their fast oxidation from tin 2+ to tin 4+. And so this gives way to higher bulk and surface defects. It's been shown recently that the partial substitution of tin with germanium fills the high concentration of tin vacancies and reduces surface defects, leading to improved stability. So it's important that we understand the bulk and surface structural defects properties of tin-germanium alloy perovskites so that we can further stabilize and increase efficiency of tin-based perovskites. And so the first thing we did in my project was synthesize an Fa cesium tin halide perovskite and study the effects of different spin coating procedures and anti-solvent and on the perovskite formation. And so we found that using anisole as our anti-solvent and a two-step slow then fast spin coater setting indicated by this 5,000 RPM resulted in higher absorbing film. And so in this composition, we also used two known antioxidants, tin fluoride and tin powder. But to further decrease the formation of tin 4+, we added tin oxalate in the precursor solution, which has shown to act as an antioxidant in perovskite nanocrystals. When comparing the film with and without the addition of 10% tin oxalate, we found that both samples emitted at the same wavelength and had the same band gap of 1.34 electron volts, meaning that the electronic structure was not altered by the addition of tin oxalate. Samples with tin oxalate also showed higher photoluminescent intensity and higher lifetime, passing a 0.25 nanoseconds and having a 3.59 nanosecond lifetime. And so after finding this recipe with tin oxalate, we looked at further improving stability by alloying germanium with tin in different ratios to passivate defects. And so looking at UV-vis, as expected, an increase in concentration of germanium in the structure showed consistent blue shift. And we suggest this is due to the lower ionic radii of germanium. And so this blue shift is consistent with the blue shift that was shown in the photoluminescence. To look at the difference between emission and morphology in tin-germanium alloy perovskites and the reference, we looked at film under hyperspectral microscopy. And so compared to our reference, samples which contained germanium showed areas of blue shifts in emission, meaning that there was higher concentration of germanium in some areas of the film and therefore higher heterogeneity. And so these samples with higher concentration of germanium exhibited longer stability as they showed a high photoluminescent emission after 1 day of aging compared to samples with lower concentration and the reference. And so to conclude, it was found that using anisole as anti-solvent and a two-step slow then fast spin coating procedure, as well as the addition of the antioxidant tin oxalate and 10%, resulted in better performing tin-based film. And when adding higher concentration of the germanium, we also saw a blue shift, an increase in heterogeneity, longer stability in tin-germanium alloy film, suggesting that germanium has potential in passivating surface and bulk defects in tin-based perovskites. And so future directions include improving surface defect passivation by the introduction of organic ligands, and also exploring germanium doping in perovskite nanostructures instead of in thin film like we did here. And so that concludes my presentation. I'd like to thank the REU Clean Energy to Bridge REU program, and also all the members in the Ginger Lab who have really enjoyed being around, especially my mentor Margarita, and my PI David Ginger, who gave me this extraordinary opportunity to work with perovskites. I hope you enjoyed my presentation and have lots and lots of questions about perovskites. Thank you.